Now, just like the other approaches that we've talked about so far, there are certain assumptions associated with general linear models that need to be met in order for our inferences to be appropriate. Now, with general linear models, there are assumptions associated with the two different parts of the model. One is referred to as the structural part of the model, and the other is referred to as the residuals. So in the structural part of the model, we're talking about the way the response variable is related to the different predictor variables. So our first assumption then from the structural part of a general linear model is that the response variable is a continuous variable, that y, or response variable, depends on one to many predictor variables, and that our response variable is linearly related to these predictor variables. And what I mean by this is that we can make some nonlinear relationships linear by transforming them, for example, with a log transformation, or we can explicitly model the nonlinearities using quadratic terms. But in this case, the nonlinear relationship overall is represented by a linear combination of terms. And it's just the quadratic term that makes the overall relationship nonlinear. But what we can't handle in general linear models are fundamentally nonlinear relationships that can't be linearized, either through a transformation or a quadratic term. So for example, Michaelis-Menten kinetics equations or von Bertalanffy growth models. So how might we detect nonlinearity in a general linear model? Well, here I've shown a nonlinear relationship between hypothetical data with our response variable and our predictor variable, where we've just fit a linear regression to these nonlinear data. And it's a little bit hard to see from the plot of the raw data, but it becomes more obvious in one of our diagnostic plots, where we plot the residuals of the relationship against the fitted values, and we can see quite a clear pattern in these residuals. So these residuals don't represent a cloud or a straight line, but instead represent a U shape, where lower values for our fitted values and higher values for our fitted values tend to be underestimated, meaning that we get positive residuals. But in the middle part of the model tends to overestimate the observed values, so we get negative residuals. Okay, so because of the nonlinear relationship here, we're getting positive residuals at low and high fitted values and negative residuals at intermediate fitted values. And so when we're assessing this diagnostic plot for our assumption about linearity, we're looking to see whether there are any observed patterns in the residuals. And this fitted line in red helps us to visualize what patterns might exist in these residuals. So this particular observed pattern would be a problem. The other set of assumptions associated with a general linear model refer to the residual end of the model. The first assumption is that the residuals are normally distributed with a mean of 0 and a standard deviation that is consistent, represented by sigma I. The second assumption is that the variance in these residuals, sigma I, is constant across all predicted values, and this is referred to as homoscedasticity. If this assumption is not met, then the model is referred to as being heteroscedastic. And this might occur because the variance in the residuals changes across fitted values, or the variance in the residuals differs among our different levels of a categorical predictor. Third, the residuals need to be independent of one another, so that we can't have associations between residuals because of either some autocorrelation in the observations or some other reason why there is a lack of independence among observations. And finally, the fourth assumption is that there's no collinearity of predictors. What collinearity of predictors means is that the predictor variables themselves are correlated with one another. We won't go into this in a lot of detail here, but we'll come back to this a little bit later on about how we might deal with this situation where we have some predictor variables that are correlated with one another. So we can assess the normality of our residuals from our general linear model using our standard techniques, like a histogram of the residuals or a QQ plot of the residuals. Now, just like when we were talking about our linear regression, we can assess the normality of our residuals using QQ plots. This is an example of a good QQ plot where the residuals are normally distributed. If we get a real bend in the residuals, that could be indicative of residuals that are log normally distributed. And here we have examples of platykurtic and leptokurtic residuals corresponding to a situation where we have a distribution of residuals with tails that are too long or tails that are too short, which is the equivalent to being too uniform. Now, general linear models are fairly robust to the violation of the assumption of the normality of residuals, as long as those residuals are reasonably symmetrical and not overly skewed. But if the residuals are heavily skewed, we should consider performing some sort of transformation of the data or to use some other approaches like something called a generalized linear model or non-parametric tests. We can also get long tails in our distribution of residuals if we have outliers. A normal distribution assumes that the tails of the distribution are reasonably small and that we should not be seeing observations that are more than 3 standard deviations away from the mean. These outliers, or very extreme residuals, can heavily skew our parameter estimates. And we can detect these residuals by performing residual plots or looking at box and whisker plots of our residuals, or perhaps by looking at Cook's distance plots, which match together an observation's residual together with its leverage. And this combination of a high leverage with a high magnitude residual suggests that this particular observation has a high influence on our final result, which is measured as its Cook's distance. When we have outliers in our data, the first thing we want to do is to go back into our paper trail of data collection to try and determine whether this was simply a data collection or transcription error. If we can find evidence through our notes or our data books that the data that were entered into the computer were in fact entered in error and do not match up what's in our data books, then we can simply correct this error. But if this can't be confirmed, we need to be extremely careful, because including this outlier in our data set could have a very large impact on the result, but excluding it could be removing meaningful information. And so there are severe consequences to either leaving an outlier in or taking it out. And so you really ought to proceed cautiously when dealing with models that include outliers, or in situations where we exclude outliers from a particular analysis. It's important to note that if you do remove any data from your statistical analysis, it's unethical to not report this in your scientific paper or presentation, and to provide some justification for why these observations were removed. When we have categorical predictors, we can test for homoscedasticity in our residuals by comparing the residuals categorized in each of the different levels of our categorical predictor. So here we've plotted the residuals from a factor that has 8 different levels in it. And you can see that the variance in the residuals goes down quite a bit as we go from factor level 1 down to factor level 8. So we can visualize this using box plots, or we can explicitly test for heteroscedasticity across levels in a categorical predictor using a Levene test. When we have continuous predictors, we can check the other 3 assumptions from the residual part of our model. We can test the independence of error terms by looking for evidence of autocorrelation. We can plot residuals against fitted values to visualize whether the variance in those residuals changes across fitted values, and to look for patterns in those residuals to assess whether our assumption about a linear relationship between predictors and our response is appropriate. So when we plot our residuals against our fitted values from a model, what we want to see are a cloud of data points with no particular pattern and no particular shape, other than perhaps an ellipse. It's normal for the variance in the residuals to decline a little bit at lower and upper ends, but it's not normal for residuals to take a cone or triangle-shaped pattern like this, where there's evidence then of heteroscedasticity, where the variance in the residuals is increasing with increasing fitted values. Heteroscedasticity could also be represented by the opposite, where we have greater variance in residuals at low fitted values than at high fitted values. And this sort of pattern in the residuals is inappropriate. We can also test for the evidence of nonlinear relationships using these same residual plots, where patterns in the residuals against fitted values like these here are indicative of a nonlinear relationship. Here, the model tends to overestimate very small and very large values, resulting in negative residuals, while the model tends to underestimate intermediate values, which results in positive residuals at the intermediate fitted values. Now, if we find there is heteroscedasticity in our residuals, then in our ANOVA type design, or where we have categorical predictors, these sorts of approaches are reasonably robust to this violation of this assumption, as long as our statistical design is relatively balanced. That is, that we have a roughly equal sample size in each of the different levels of our categorical predictor. In the case of continuous predictors, regression type models are reasonably robust, but what they tell us is that one side of the regression is figuring in more heavily into our estimates than the other end of the regression. And so we might get some bias then in our parameter estimates. Most of the time when we have heteroscedasticity in our residuals, then we can fix this problem by performing an appropriate transformation to the data. So in summary then, the assumptions of our general linear model are fairly similar to the assumptions that we've already encountered for regression and ANOVA. The predictors must be linearly related to the response variable. The residuals must be normally distributed with constant variance, and our observations must be independent of one another.